Okay, good morning. This is Professor David J. Delosreyes. Okay, the date for tonight or for this morning will be September 17, 2023. The time is around 12:20 a.m. Okay, my topic for this morning will be a long video format discussion on this will be AC machines, and we are now on lesson number 13. So for those of you who are following my channel on the discussion AC machines, this will now be lesson number 13. Okay, let's proceed. The title of the topic for this morning will be alternating current machines, and this will now be lesson number 13. We are running smooth. Okay? uh, we do it gradually, but we are running smooth. Okay, the title of the topic will be example problem on RE, XE, Z sub E of transformers. Meaning it will be a problem involving the computation of the so-called equivalent resistance, equivalent reactance, and equivalent impedance for transformers. Okay, I will try to give you a figure. The figure is actually the figure of the problem I will be discussing for this morning. We are given a single phase transformer. The total apparent power of the transformer is 100 kVA. The input voltage on the primary is 2400, and the output voltage on the secondary is 240 volts. Frequency of the primary 60 Hz, frequency of the secondary 60 Hz. Okay. I put the so-called impedance drops for both the primary and secondary so we could visualize it. This should be RP, meaning the small resistance on the primary side, reactance on the primary side, that is for the winding. Right? On the secondary side, it will be small r with the subscript s, meaning the internal resistance on the secondary side. With that's S is subscript S is refers to secondary, and the next one will be reactance on the secondary. The current moving out from the secondary is I sub S, and the current coming in from the primary, coming from the transmission line, is I sub P. Okay, I will try to read the problem. So the figure of the verbal problem is this one, so I will now try to read the problem. A 100 kVA distribution transformer, okay, with the voltage rating 2400/240, okay, 60 cycles, meaning 60 Hertz, has the following constants, okay. The internal resistance on the primary side is 0.42 ohms. So subscript P here refers to primary. The internal resistance on the secondary side, that is R with the subscript S, will be 0.0038 ohms. For the reactance on the primary, it is 0.72 ohms, and the reactance on the secondary is 0.0068 ohms. The problem got a question and calculate the values in primary and secondary terms, okay? What is being asked is a capital letter R with the subscript A, meaning the equivalent resistance of both these parameters here. And the equivalent, what they call this reactance, and the last requirement is the equivalent impedance, okay? The given condition, we must have to bring out our solution using the primary terms and using the secondary terms. Okay, I will try to annotate tonight the importance of the computation of RE, XE, and ZE. This is important in the computation of the so-called percent regulation of transformer. Percent regulation is actually what they call this a grading system for transformer, so we could say if the transformer is efficient enough. So if the percent regulation is high, okay, there will be a problem with the transformer. If the percent regulation is low, okay, it is a good transformer. Later on, when we will bring out a problem regarding percent regulation, we could visualize what I'm saying, that a low percent regulation is a good transformer and a high percent regulation is actually a bad transformer. Okay, let's try to bring out the solution. For the solution of this, okay, we will be using the concept that the one that was discussed from lesson number 12. Okay, solution. In primary terms, let's try to compute for the equivalent resistance, reactance, and impedance in primary terms. Okay, so the first requirement here, okay, I will read it. Capital letter R with the subscript E, again with the subscript P, meaning the equivalent resistance referred to the primary. The one that was derived the last time around is this one, right? If we are talking primary values and we are talking resistances, to combine RP and RS in terms of the primary side, it will be an R sub P plus E sub A square times R sub S. Okay, I derived this one the last time around. Right? So this is now just a matter of direct substitution. The problem is if you could not recall your equation, right? I will repeat it. The equivalent resistance referred to the primary should be equal to the resistance of the primary plus the resistance of R sub S referred to the primary. For it to be referred to the primary, it should be multiplied by the ratio of transformation square. Okay? Okay, let's try to compute for the ratio of transformation. By definition, ratio of transformation is actually the induced voltage on the primary over the induced voltage on the secondary, and this should be equal to the secondary current all over the primary current, right? Where is E sub P? E sub P is here, right? E sub S is here. Okay? But what is given is the terminal voltage here. It is not EP. Okay? So, to compute for the ratio transformation, we should know E sub P and E sub S. But we do not know this value for the meantime. So, what do we do? Assume for the meantime that BP is equal to EP and BS is equal to ES. Right? So if we try to divide this one, by definition, ratio transformation is the induced voltage on the primary over the induced voltage on the secondary. Okay? But since EP and ES are not given, we will equate these two values now. So instead of looking for the value EP over ES, we just use the value BP over BS. Because BP is actually 2400. The one coming from the transmission line. And the output is actually termed to as BS. So instead of taking the ratio EP over ES, it is safe to say that we will just, to compute for the ratio transformation, we will take BP over BS. So I place it here. BP is 2400, BS is 240, so the ratio of transformation is actually 10. That is a step-down transformer. Why step-down? Because the input terminal voltage is 2400, and what comes out is only 240, so this is a step-down. Meaning to say, if you've got 2400, and if the ratio of transformation is 10, okay, the output should be 2400 over 10, it will just be simply 240. That's why the ratio transformation is 2400 over 240, which is 10. Okay? So the given problem is actually step-down transformer. This is the one we are using in the so-called distribution transformer, the one that's hanging on the post, the one that goes to our service entrance. Okay? But the voltage coming from the service entrance here in the USA, there are some voltages which are 240, there are voltages which are 120. So it depends on what you call this, the nature of your load. If your load may be an air conditioning unit, which is 240, your coming or your service entrance voltage should be 240 instead of 120. Okay, I will repeat it. The given distribution transformer is step down. 2400 to 240. Okay, the ratio of transformation is there. Okay, let's proceed with the computation. That's a little bit, storytelling, but we are discussing concept. So to compute for the equivalent resistance referred to the primary, it should be R sub P plus A square RS. So we now know A, right? So the square of A is 100. And what is R sub P? We are given R sub P. It's 0.42. Right? A square will be 10 square, that will be 100. RS is 0.0038. So this is multiplied by 0.0038. If we try to add this, it should be 0.42. We move this one 2 places to the right, it will be 0.38. 0.42 plus 0.38 is 0.80 ohms. So the equivalent of this R sub P and R sub S referred to the primary is 0.80 ohms. Okay? The reactance, it will still be the same formula. We just, change the designation of R to X. So we are now computing the equivalent reactance referred to the primary. It will be XP. Same formula. But we are computing per reactance, so this should be A squared times X sub S. XP is 0.72. A squared will be 100. XS is 0.0068. This is 0.0068. So we move this, the decimal here 2 places to the right. So it will be 0.72 plus 0.68. The equivalent reactance referred to the primary is 1.40 ohms. Okay? To compute for the equivalent impedance, we know that impedance is the vectorial sum of R with the subscript A primary and X equivalent referred to the primary. The vectorial sum of the REP and XEP is actually ZE with the subscript P. Okay, so we now know this one, we now know this. You could use the tangent law, we could do that, but since we are only solving for the magnitude of equivalent impedance referred to the primary should be the square root. Pythagorean principle. 0.80 square plus 1.40 square. Taking the sum of the squares of this, it will be the square of 2.6. And the square of 2.6 is 1.61 ohms. So this is 1.61 ohms. Okay? So we are now given the equivalent resistance referred to the primary, equivalent reactance referred to the primary, equivalent impedance referred to the primary. That's why our topic for tonight is how to compute for RA, XA, and CA. Okay? First solution is by using the primary terms. In secondary terms, it will be a different story. We will be using the derived equation the last time around. That is for the secondary values. The equivalent resistance referred to the secondary. We are now taking to the secondary side. So to add this two group of impedance, okay, and we are now on the secondary side. We will maintain this one, but we must have to change the value of this to be referred to the secondary by dividing by a certain factor. So I will read it. The equivalent resistance referred to the secondary will be RS, and the equivalent of R sub P, if we try to refer it to the secondary side, it will be R sub P over A square. Okay? This is now referred to the secondary side. Right? We maintain the RS, then we take the converted value of this referred to the primary by dividing it by A square. Okay? So, substituting values, this should be 0.0068. XS is 0.0068. Okay, XP is 0.72. If we try to refer this to the secondary, we will divide this by A square, which is 100. So it will be 0.0068 plus 0.0072, and that will be 0.014 ohms. Okay? The values are lesser compared to this primary because we are on the secondary side, because the transformer is a step down. Okay? For the reactance, I am mentioning reactance. For the resistance, RS is 0.0038, RP is 0.42 divided by 100, 0.0038 plus 0.0042 will be 0.008 ohms. Okay, that's for the equivalent resistance referred to the secondary. For the reactance, I will repeat it. 0.0068 plus 0.72 divided by 100. What comes out is 0.014 ohms. Again, for the equivalent impedance referred to the secondary, again, draw your vector diagram, right? This is RE with the subscript S. This is XE with the subscript S. And this will now be the equivalent impedance referred to the secondary. So we are given this value here. We are given this value. We are just interested in the magnitude. So using Pythagoras principle, it will be the square of 0.008 square plus the square of 0.0014. Okay, I will just give you the final answer. It's 0.0161 ohms. Okay. So we are now given the value of RE, XE, and ZA referred to the secondary side, and the next one is referred to the primary side, the first one, and the next one is the secondary side. Okay, example number 2. At least we now know how to compute equivalent resistance, reactance, and impedance if referred to the primary and secondary. We will be needing these values in problems involving percent regulation. So if the requirement of the problem is percent regulation and you do not know how to compute for RA, XA, and ZA, you've got a problem, right? So this is just a requirement for problems involving percent regulation. Okay, so we are taking it gradually, right? The needed concepts on how to compute percent regulation is being discussed now. So when we go to problems involving percent regulation, you know this, right? Okay, example number 2. Am I still on camera? Using the data in example number 1, calculate the voltage drops in the primary and secondary terms. Oh, that's an easy one. We now know the equivalent resistance, reactance, and impedance. The problem is just asking for the voltage drops due to this. What is needed? It will be the current, right? Because voltage is actually equal to the product of Ij, or voltage will be equal to the product of I times R, or voltage will be equal to the product of I times X. Okay, so these are the one being asked, right? We now know ZA, we now know RA, we now know XA, so the only problem now is the current. Okay? And from the definition of apparent power is the product of voltage times current, and that is actually equal to 100 kVA. For the given problem, the product of voltage in ampere is 100 kVA. It was given on the problem, right? 100 kVA. So, if we know the voltage, we could compute for the current. Right? So, using secondary values, IS now will be kVA over V voltage, right? If we try to compute per ampere, this should be all over voltage. Okay? No more voltage here. And this is I, actually I. and this is voltage. So meaning current is the apparent power, we should convert it to volt ampere. So there is a multiplier times 1000 over here, over voltage. So using the secondary values, if we try to compute for the current on the secondary side, it will be the given kVA times 1000 over Vs. The given kVA is 1000. Am I still on camera? 100 times 1000 over 240. Okay. What will come out will be 416.67 amperes. It's a high current. Why it's high current? Because the voltage on the primary, secondary is just on the 240. Okay, multiplied by 417 approximately. Okay, so this is a low voltage on the secondary, so the current should be high. Right? On the primary side, if we try to compute for the current on the primary side due to the 100 kVA, it will be an IS over A, right? Because the definition of A is actually EP over ES, and this is actually IS over IP. And if we try to remove this, okay, IS now, or IP, will be IS over A. So this will be 416.67 over 10. The voltage on the primary side is only 41.667 amperes. Why it is slower? Because the voltage on the primary side is 2400. So supposed to be the current is actually smaller. Right? Smaller. So you see the difference? High voltage, smaller current, low voltage, high current, for them to be equal. Okay? So we now know the current on the primary side to be 41.667 amperes. So if we now try to compute for the voltage drops on the primary and secondary, primary first, IP times REP, this should be equal to. Easy money now. Primary current is 41.667. REP is 0.80, right? 480. Where is REP? 0.80. Right? The voltage drop due to the internal resistance of the winding on the primary is 33.3 volts. For the voltage drop due to the reactance of the winding on the primary, it will be same current times the reactance equivalent on the primary, and that is actually 1.4. So this should be 41.667 times 1.40, that will be 58.33 volts. Okay? So actually the voltage drop is almost maybe $60, 60 volts if you try to compute it. Because this is 33.3, this is 33.3, and this is 58.3. Okay? It's almost 60 volts maybe if you try to take the vectorial sum of these. But the problem is not asking for the value of the overall voltage due to the hypotenuse. This is the voltage drop due to the resistance, voltage drop due to the reactance. That is for the primary. For the secondary, we will just replace the current. It should we will be using the current on the secondary side. The current on the secondary side is 416.67 times 0.008. RAS is actually 0.008. Right? It is 3.33 volts. IS, XES will be same current for 16.67, and XES is actually 0.014. This is times 0.014, it is 5.83 volts. So as you can see, the voltage drop on the secondary are smaller compared to the primary side, because the voltage on the secondary side is smaller than the primary side. So supposed to be the drop on the primary side is greater than the drop on the secondary side. So these are our answers. Okay. The next time around, we will be continuing this problem, and I will give you a problem on how to compute for the percent regulation. If the power factor at the secondary side is unity, lagging, or leading. So we could see the difference. And we will be using the vector diagrams that was discussed from, I think, lesson number 11. Okay, that's it, guys. So this will be an example problem on how to compute for the equivalent RA, XA, and ZA of transformers. Okay? And these are needed in the computation of the so-called percent of regulation. Okay. This is Professor David J. De Los Reyes. Good morning from Los Angeles.